Technology is smiling class. That's available all day, so way more flexibility. They will be able to help you all out. Good to go. So help room, please go there. One of the reasons they are so useful compared to me is it has been, let's do the math, again, age myself a bit, 12 years since I learned this content for the first time. 12 years since I learned it for the first time. That's a long time. I don't remember, as much as I may want to try, I don't remember the exact struggles and experiences that you all are going through. 12 years from now, you'll forget the exact struggles and experiences you're going through now as well, for good or for bad. Maybe that'll be a good thing. These students learned it very recently. They know exactly some of the challenges you're going through, exactly some of the concepts that are difficult. And so when you talk to them, they're going to be really well equipped to be like, hey, I remember going through that. Here's some strategies that helped me. Here's some things that helped me. So again, really cannot hype that help room enough. Please make use of them for the problem sets. They are a wonderful resource. Okay, so we talked about the discussion sections. I will update those in a week. The quiz grades, let me talk about those real quick. So I looked through them. I'm pretty darn happy with them. I think the scores ranged on average between 3 and 5. I don't know what the exact average was. If you are getting a 4 on the quiz, that's kind of your target. Target is 4. 4 is great. 4 out of 5 questions, you're in a good spot. If you're getting 5, obviously that's excellent. If you're at 3, that's okay. But you're going to definitely want to go back. I posted the solutions for the quiz. Let me show you all where that's at. So moving forward, I will always do this. If you go to the Files tab, it's in the same place. Every one of my resources is all in the Files tab. If you go to week 1, and there was a bit of a typo, or that the file I uploaded wasn't quite the right one, so I've addressed it, and it is fixed as of an hour ago. 2 of the problems were old problems, and I just had to upload the right file. If you all go to this, it's a PDF. It's got the entire thing worked out. I will continue to do this for every quiz. Obviously, I will upload this after the quiz window ends. So, heads up on that if you're confused on how to do it. That resource is available. The last thing I want to point out is you all notice your quiz grades did not factor into your final grade yet. The reason for that is the quizzes, I have noted they are graded out of however many questions there are. There are 5 questions. So according to web courses, they're graded out of 5 points. If you look at every single one of our quizzes, 5 points, 5 points, 5 points. The reality is, if I scroll down here, I have a column. This is the one that's going to factor your grades. It's called adjusted quizzes. The reality is I'm not grading your quizzes out of 5 points. I'm grading them out of 4.5 points. Very slightly different, but the result is it'll boost your grade a bit. So instead of, say you got 4 questions right out of 5, instead of getting an 80%, let's just do the quick math. Instead of getting an 80%, you get a 89%, which feels a heck of a lot better than an 80%. The other benefit is if you got all 5 questions right, you get above 100%. So that's nice, right? So these take, I'm going to upload, like I move them to the adjusted quizzes. Maybe I'll do that like every 2 weeks or so. But just know that your grade, that's why your quizzes aren't accounted for in your web courses grade. Your grades aren't accounted for it because I have to manually download the Excel file, transfer them all to this other column, re-upload it. It takes a little bit. I just haven't done it yet. So, any questions about discussion, questions, quizzes, problem sets, anything like that? Okay, cool. Let me double check that this is still working. For those that are on the live stream, apologies for the delay. The reason for the delay was that, again, you all get to see behind the curtain. Let me get this fixed real quick. Give me just a couple seconds. I have to log into this. It doesn't save my password, and I don't want you to see my password. So, apologies for the delay. Today we're going to be talking about potential. Potential is, and what electric potential energy are. These 2 ideas. We need to apply them to systems to see how things will behave. And we need to identify how electric potential can be practically used. That's going to especially come up. I'm going to give you all a sneak peek. Another name for electric potential is voltage. You've probably heard the word voltage. You can already think of some practical applications for voltage, batteries, electricity. So we need to talk about it first, and we're going to start to get into circuits within the next 2 weeks or so. So next week we'll start to kind of introduce circuits, and then the second week after that, we'll finalize it. Reminder to you all, because I haven't said this yet, we are going to, remember your second quiz is due at the end of this week. That's going to be on electric fields and electric multiple charges contributing to electric fields, so make certain you all have done the problem set problems. Just keep that in mind. Remember, every week there's a quiz. Every week there's a quiz. All right, so first clicker question from Physics 2053. I'll go ahead and start it, just in case you have it on top of your head. Spend a few seconds calculating it. This one does involve a little bit of calculations. It's conservation of energy. From Physics 2053, you drop a water balloon with mass 1 kilogram from the top of the physical sciences building. This is PSB, it's a building here on campus. And you're hoping to splash your friend as he walks by. What value is the closest to the speed at which the balloon hits the ground? You all may recognize this problem. Great news. If you don't, I'm not going to ask a problem like this on your quizzes or tests. It's not going to come from the problem sets. I am bringing up this problem because we're going to use these concepts. We're going to use the ideas behind conservation of energy today. And so if you don't remember this at all, don't worry. We're going to kind of see it enough that it should be able to get you kick-started in the right direction. But if you do understand this, you'll be kind of at a little bit of an advantage. The content we're covering today will be a little easier for you. I will straight up tell you, you do have to actually calculate this. There's no way you can really just do this in your head. If you can do it in your head, tell me how, because I don't know how to. And we'll go all the way to 2 minutes. Give you all the time to think through it. Remember, if you miss these questions, that's okay. It's not going to penalize your grade really at all. The quicker questions, if I ask 100 of them, at the end of the quarter, I'm only grading out of that 75. And that 75% is just, if you do all of them, you get that full 75% just from participation. So don't let these quicker questions stress you. These are just kind of a way for me to pad the grade for you all a bit and give you some ways to engage with the class other than just listening to me chat the whole time. All right, so 10 more seconds. 5, 4, 3, 2, 1. All right, so I'm fairly encouraged. Either if you've done this before, you all did some quick maths. Good amount of you got it right. Nice work. If you didn't get it right, that's okay. I'm not going to go through the full kind of process for how to solve this problem. I'm going to do it quickly because, again, I'm not trying to teach you all this. This is from Physics 1. But I do want to remind you all, conservation of energy says that the energy you start with, the energy initial, equals the energy final. And so when we look at this problem, what kind of energy do we have to begin with? In the beginning, we have potential energy. We're up high, but we're not moving. So we have no kinetic energy in the beginning. By we, I mean the water balloon. The water balloon is not moving at the beginning, but it's up high. So that's what we start with. At the end, it reaches the floor. So we're no longer up high, so we lose all our potential energy, and it all gets converted to kinetic energy. There's no potential energy at the end because it's all the way on the floor. We remember our equations of potential energy and kinetic energy because you all have far better memories than I do. And I sincerely mean that. You kind of have to for any medical related thing. For physics, you don't. That's why I'm in that field. So potential energy is mgh, initial, and then equals 1/2 mv final squared. Really fun thing with conservation of energy, if you didn't see this before. Turns out you don't need the mass. They cancel out on both sides, so it makes the calculation a little easier. Gravity is 9.8. Height is 10 meters. 1/2 is 1/2. We're solving for the final velocity. If we rearrange this, we get the final velocity. We can multiply that 2 over, and then we can do the square root. So we get the square root of 2 times 9.8 times 10, and we do get 14 meters per second. Great. All right, so again, the reason I showed this is this setup of an energy initial equals energy final. We are going to use that concept today. We're not only going to use this, we're also going to use our definition of kinetic energy. That's going to come up with some of the problems that we have to solve. The thing that's going to change for you all is my potential energy will no longer be due to gravity, but instead is going to be due to charges. If you all remember from Physics 1, energy is just another way to look at reality. We've talked about fields so far, just like in Physics 1 you talked about gravitational fields, and you talked about kinematics, but energy is another way for us to conceptualize reality. And the really nifty thing with energy is it can be used to explain everything with one simple rule. Everything in the universe wants to get to a lower potential energy. You can use that to explain anything that happens in the universe, as long as it's not relationships with other human beings. Those are much more complicated. But as far as physical things, everything wants to get to lower potential energy. It turns out that there's more than just gravitational potential energy. There's also electric potential energy. But the same logic applies. It wants to get to lower electric potential energy. So, another quick thing. See your all's memory from your previous class from Physics 2053. What quantity, what variable, what value is determined by a change in potential energy that's acted on by a force? So there's a change in energy, and this change in energy is also equivalent, I'll give you all a hint, to if I multiplied a force times a distance. These two things were equivalent. This definition, whichever answer it is up here, is it spring constant, displacement, acceleration, work, whatever this answer may be, it is equivalent not only to the negative change in potential energy, but it is also equivalent to a force times the distance, assuming those two things line up with each other. That the force that we're acting on is in the same direction as the distance we're going in, or at least a component of it is. I'll give you all to like 110. There's not really anything to do here math-wise. It's just straight up definition. 5, 4, 3, 2, 1. And yet again, pretty good memories from y'all. It is work. Again, if you don't remember that, that's okay. We're going to cover it today. Just trying to kind of pull that knowledge in because we're going to see that today. We're going to see work again. For good or for bad, it's going to come up. Work is defined as the change. If you all don't recognize a symbol, may not be in a fraternity or sorority. That is the capital Greek letter delta. It means change. Change in potential energy. It's the negative of it. It is also equal to the force dot the distance. There's technically a dot product there. And if you remember from our dot products before, those are the same. I'll write out that definition. We're going to see it again today. F d cosine theta. We saw the dot product with flux before. We're going to see it again at various points. It's a way to multiply vectors. Okay, cool. Again, if you don't remember the stuff, it's going to come up. We're going to see it again here. So it's all going to work out. Don't let it stress you. All right. So we have a set of interacting particles. How is work related to potential energy? How is work related to force? I literally just wrote that. I'll write it again here. Work is the negative change in potential energy, and work is that force dot distance. And we can put that. So this is exactly what I had before, but I'll put it here in case you look at these later. If you didn't know, I think most of you do, but in case you didn't, remember these slides are all online. I highly encourage you all to download them before class. It'll make it easier for writing notes. You're welcome to write your notes from scratch, but if you download the slides, you can just add to it, and it'll hopefully save you some time. All right, so we see that here. Again, this is just reiterating what I just said. The force times the distance is going to give us that work. Okay, so where's Dr. James going with this? More of the same. We're going to connect it to what we talked about before. Remember that we talked about force, talked about it a few times already. We defined it as the force between two charges. We saw Coulomb's law, so we can even put that on here if we'd like. Force was also equivalent if we had two charges, to K1, Q1, Q2 over R squared. So we've seen that before, but we also saw it with the field. And we saw it as the charge times the electric field. The charge that is experiencing the field. Not the one making the field, the one that is experiencing the force. This is the charge experiencing the force. And so, if we use our definition for potential energy, so you're wondering maybe what the heck's going on here. These are both work. Work was potential energy. Work was also force times distance, so that means you can set them equal to each other. Previously, I had the negative sign in front of the potential energy, but I could easily move it to either side. That's fine, I'm allowed. Negatives, I can make one side negative, or I can make the other side negative. Either way is fine. Previously, I had it over here. I just moved it over. That's fine. So the change in potential energy is going to be Q times the electric field, dotted with that distance. All of this is just helping us derive our final equation. So we're getting to the punchline. We'll get there in a second. So our change in potential energy for charges, if we want to say, hey, how much did the energy change? We take that charge, we multiply the electric field that it's in, and we dot that with the distance. Now this gets a little tricky when our electric field is changing. When our electric field is changing, this is where calculus would come in, and we would have to integrate over that. Again, I'm not going to have you all do that because it's not calculus. So you are going to see some equations today where I can't really derive it for you because it involves calculus. I have to integrate it. But that's the reality. We would have to do that. Now, let's imagine a beautiful problem where the electric field does not depend upon distance. It's the same everywhere, no matter where you are. If only we had a beautiful set of charges that if we arrayed them in such a certain way, the electric field doesn't depend upon distance. Oh look, it's that infinite plane. If you all remember the infinite plane, I gave the electric field due to the infinite plane last class. The electric field due to an infinite plane was sigma, which is the charge density, charge per unit area, over 2 epsilon naught. Reminder to you all, sigma here is the net charge divided by the area of the plate. Nowhere in that equation do we have how far away you are. This was that really interesting thing about this problem in particular. It does not matter where you are. I could be here, I could be here, I could be way up top. It does not matter. The electric field is the same everywhere, which is very convenient for this problem where we need where we're going to use that potential energy to find the distance it's going to be going. So this problem says an electron is released from rest, a distance z above a positively charged infinite plane with charge density sigma. What is the speed of the electron just before it hits the surface? So now we're going to see that whole potential energy, that conservation of energy problem, but applied to our charge stuff instead of gravity. So let's go ahead. We said E initial equals E final. And this is where things get dicey, and I'm going to actually write out the word. Up to this point in this class, we've used E as electric field, so unfortunately I have to write the word energy now because E means 2 different things in this class, which is not ideal, so I'm just going to write the word energy. Energy initial equals energy final. When we are up here, my charge is not moving, so I only have potential energy. But not just any potential energy, I have potential energy due to an electric field. This is where this problem is the exact same as the one that you all did at the beginning of class, but instead of gravity, now it's electric fields doing the work instead of gravitational fields. So my potential energy, and originally, is going to equal my kinetic energy final. When I get down to that plate, we'll kind of lose all that energy. So let's go ahead and move to a new slide. Quickly solve this problem. I'm going to copy and paste everything over so that we can have that reference. All right, so we have our plane, we have our energy initial, and then we just quickly plug in. Oh, is that going to travel with us everywhere we go? Oh, that's cool. All right. Sometimes my PowerPoints do this, where a symbol is just going to travel. Oh, is it gone? Okay, phew. I thought I'd have to restart the program. Sometimes my symbols travel across slides. Again, technology is one thing that none of us have complete control over, unfortunately. So we said potential energy was Q, E, D. And actually, I should put this over here. I need to put this over here. So I actually have an energy initial and an energy final because when I wrote down this equation before, it was the change. Change means beginning minus end. And whether or not you realize this, you did this when you did your problem with the roof. When we were doing that original problem, you may have been like, we didn't have a final potential energy, but you did. You called it 0. And you got to decide that that was 0. You decided that the ground outside was 0. But the reality is, what is 0 height? Is it the ground outside? Is it the... If I said it's my ground right now, I'm about, well, depending on how far back you are in this room, my 0 is at my feet, and that is actually about 1 meter high compared to the rest of you all. So what is 0 when it comes to height is all relative. Is 0 my stage up here? Is 0 the floor here at the beginning? Is 0 the center of the earth? Even in gravity, height is relative. You have to define what 0 is. In this case, though, we don't have to deal with it because we're just going to subtract these two together. If we do our final minus initial, and we had a negative here, which is quite useful for us. That's going to be very important. Let's go ahead and bump this. This is a U, not a K. If I write this out here, I move the energy, the potentials to one side. We're going to see how that negative is going to be handy. To clarify, this change here should be final minus initial. This is UE final minus UE initial. That's fine. This cable got slightly tinged. And it's back up there. All right. Well, in our problem that you all wrote down, as I slowly, gently give it that sensitive touch it needs, you all notice that this one over here on the right and this one over here on the left, they're backwards. So let's just slap a negative in front of it. That's going to flip it for us. And ta-da! We have change in potential energy now. Equals kinetic energy final. So now I have my negative potential energy, change in potential energy. Try to make my U's look like U's and not K's as much as possible. Equals kinetic energy final. And you're going to see here where that negative comes handy. Why it's important that we have that negative. If we now plug this into here, I'm going to go ahead and write that over here. We have negative QED equals, and we're going to plug in what kinetic energy is, 1/2 mv final squared. And we're finally getting somewhere. We're finally getting where we can start plugging. It's all in terms of variables. I haven't given you all a problem yet where you're going to have to keep things in variables. I'm going to probably keep it that way. But just kind of showing you all the logic, connecting this problem to one you're familiar with, which is things falling down. What is the electric field due to a... So these negatives are going to cancel. Woohoo. My charge, I believe, I was very kind and I made it Q. Nope, made it an E. So let's go ahead. That Q was E in the problem, so we'll put the E there. The electric field was sigma over 2 epsilon naught. My distance is Z. So these are all variables from the problem. What was my distance? It was Z. What was my Q? It was E. So I'll jot that down up here for you all, just when you look at this later, you're like not wondering what the heck I was doing here. There you go. That's our step 1. What's our kind of givens? Those are there. All right, equals 1/2 mvf squared. Does it give us a mass? No. A positively charged, we're just going to leave it as mass of the charge. That's fine. Not a huge deal. Again, we're not actually plugging in numbers. And if you solve for VF, you do a bunch of algebra, you multiply the 2 over, you divide by the m, you square root it. I'm just going to cram that all into one big step here. So E, sigma, there's an extra 2 on top because I multiplied that 2 over. I divide by charge. I have another 2 here from there before. At this point, I just did a bunch of algebra in one step. Normally, I would walk through that algebra with you all. But for this problem, I don't really want to spend the time on it because it's not a huge deal. I'm not having you calculate a problem like this. But that's the end of the day. If I had numbers, you would plug in numbers and be able to solve it. These 2's would cancel. And so just what I want to show you all is that this problem, where we're going to get some more with numbers, we're going to get some other examples, is like the one of a thing falling. Though the exception was, instead of having MGH, I have QED. Q instead of M, D is kind of like my distance, and E is kind of like gravity. Instead of gravitational field, it's an electric field. So you can see some parallels. And what's interesting is these are two different forces. These are two different forces in reality, and yet we continue to see parallels in how the math kind of shows up. We don't have a grand unifying theory that connects the two, but we see these little hints that maybe there's something. They seem to be really similar. But who can say? Humans also like to see faces in everything. Does that mean that everything is made of faces? No. So sometimes humans just see patterns and take it for something that it's not. Okay, so look at that. We did all right. We got there. It's all written out maybe a little bit nicer than I wrote it out, but you can see here that we get the same answer. So if you prefer a little bit nicer writing, I did lose a Z along the way. My apologies there. My Z got, there it is. So it's written out a little bit nicer, but exact same thing. Okay, so we get to the punchline. We did all this jazz. Woohoo. You guys got to see that connection. We'll do some problems with numbers. Here's an equation which I told you all I can't necessarily derive for you all. I'll give you a hand-wavy derivation. But here is the potential energy that two charges have. If I have 2 point charges, how much energy is stored in that system? How much potential energy is stored in that system? It's a very nice and simple equation. And this is where I told you all, notice there is no vector symbol over that. Energy is not a vector. Which means when you're doing these problems, you don't have to break things into x and y components. You can just calculate them, add them or subtract them, and call it a day. In this case, we are going to see that positive and negatives will kind of matter. But this is our grand equation for it. The equation for the potential energy due to two charges is 1 over 4 epsilon naught, which is the same as K, Q1, Q2 over R. This may look like Coulomb's law to you, but there's no squared on the bottom. There's no squared on the bottom. So it's even nicer when you plug it in and when you have to solve for things. Everything about it just gets a little nicer. And so my hand-wavy derivation for you all, again, it's not ideal, but it's fine. It's technically, again, a little cheat. But we said that potential energy was QED. Well, let's actually, let's plug in some values for that. Let's call that one Q1 now. Let's say this is electric field due to a separate charge. We remember in our class that the electric field due to a single charge is K, this is the one making the field, over R squared. And we don't use the variable D in any of our problems. We use the variable R. And so you can see how this equation is derived. Like, again, this is a little hand-wavy. Technically, you're supposed to do an integral here, but kind of works out this way algebraically, so it's kind of nice. K, Q1, Q2, that R cancels that R. Bam, there's the equation. Woo! So you can see how we can kind of derive it, but technically we should have done an integral. Whatever. You still get there. What I want to point out to you all, it's always good to look at the boundary conditions. As R goes to infinity, this energy goes to 0. As R gets closer, this energy gets bigger. It's harder for them to get them together, or that energy may build. If I have a positive and a negative charge, it's actually a good kind of thing to mention here. When you're doing energy, because these are not vectors, when we did vectors, we did not plug positives and negatives in here. I told you all take the absolute value, assign the positives and negatives when you're adding the vectors. When you're doing vectors, you assign the positives and negatives when you're adding them. In the case of scalars, you need the positives and negatives the entire time. When you're doing scalars, you do need to put the positives and negatives. Let me go ahead and tell you all why real quick, give you a very, very simple example to clarify this. If I have two charges, one is positive and one is negative. Let's go through both cases, because this should match everything we've learned so far in class. This should match everything we learned so far in class. What should these do? Attract or repel? Spot on. We're really good at that. Remember I told you one of the rules of the universe is that things want to get to lower energy. They want to get to lower energy. Everything wants to get to lower energy. So if we use our equation here, K, Q1, Q2 over R, I already told you all as R gets smaller, as R decreases, as R goes down, the absolute, and I'm going to clarify this, the absolute value of potential gets bigger. As R goes down, the absolute value of R gets bigger. This value will get bigger. However, let's go ahead and plug those negatives in here. In this problem, my Q1 is positive, but my Q2 is negative. So if we pull that negative to the front, my potential energy, this value here, gets bigger. However, it's a negative, which means if I have a bigger negative, that is technically a smaller number. So, where do these want to move? Towards each other. What happens when they move towards each other? I get a smaller potential energy because it's negative. A bigger number here actually makes this whole thing smaller because of that negative. So, the logic still applies. If I have two positives, let's do the opposite case. If I have two positive charges and I do the exact same thing, they're both positive. I'm just kind of writing the equation as is. As R, so in this case, yes, they don't want to get closer. As they get closer, potential energy is going up because it's positive. So, it matters. The positives and negatives matter when we talk about scalars. The positives and negatives you put into the vector addition later for vectors. That's how I've been teaching you all so far. Okay, so that's just a quick concept thing. Everything we cover should make sense. All the concepts should all come together. If at any point I tell you one thing and I tell you something else and they seem conflicting, trust me, reality should not conflict with itself. Remember, things fall. Coulomb's law says that they attract, or Coulomb's law says they repel. They attract if they're opposites, they repel if they're the same. That should apply no matter what paint job we put on this thing. And if I tell you that potential energy, things when it gets the lowest potential energy, they should match that. If not, then I'm telling you something wrong. So, at any point, if I seem like I'm telling you two conflicting things, come up to me and ask, and I can help clarify where maybe some miscommunication is happening, because they should all line up. Okay, so let's go ahead. No, we're not going to work through this, because it's just going to be more of a derivation, but it's that same idea that we talked about. You can see the derivation here. We're just going to walk through it. I'm not going to do it myself. This is where I told you all there's an integral. Remember, I warned you integrals are a thing because of the charge. We have to do an integral here because the field is changing over time, over distance. Again, don't worry about it. All this is showing you is that you get the end result that I already showed you. This is the calculus derivation for those that want it. It's here. Behold it. Wow. We'll give it its 2 seconds of glory and move on with our lives. All right. So, electric potential energy. Here's a nice little slide that's got kind of all the pieces together. If you didn't already have it down, nice and organized. What is electric potential energy? It is the potential for a system to do work due to electric forces. Our variable is U, lowercase e. We have to clarify what our potential energy is. Previously, when you all were doing physics 1, you had a U with a lowercase g for gravity. Now it's E because it's the electric field. The unit is still joules. Joules is the unit for energy. Our equations that we've seen so far, they're all here, and I have emphasized for you all that the bottom is not squared. Ironically, I have trained you all very well to square the bottom. All caps bolded, 3 exclamation points told you to square the bottom. Well, now don't square the bottom. This is this is where things can get a little like, you can make some mistakes. If I'm saying force, or I'm saying electric field, square the bottom. Use the right equation for the job. Be careful when you're solving things. They're very small differences, but they make a big difference. Like, just a little 2 on the bottom will make your answer drastically off. So, be careful when you are solving problems. I've warned you all that we are humans and we'll make mistakes. And trust me, it's going to happen to you all a lot. My dream for you all is that you make all those mistakes before the test, before the quiz. You get them all out of your system, and then you take the test or quiz and you don't make the same mistake again. So, the bottom here is not squared. Please, please, please don't square the bottom and make that silly mistake. You'll feel really bad later. The silly mistakes are the ones we feel the worst about because like, I should have known better. Okay. So, again, just a recap of everything I've shown so far. All right, moving on. There's that traveling sick. It returns. It's like a ghost. Pops when you're not looking. So here's a clicker question for you all. Using that equation that we I just showed you, if I have two charges, both positive, what's going to happen to the net potential energy if I double the distance between them? If I have two charges, both are positive, what's going to happen to the net potential energy if I double the distance between them? So, use that equation. It's kind of like the electric field ones. Yeah.
Just to clarify,
Mm-hmm.
for the 2-point question, is the R12 R1 times R2?
It's a great question. To clarify here, if I ever put numbers in the bottom like this, it's kind of like an adjective. So this is the distance between charge 1 and charge 2. R12 here is the distance between R1 and R2. In fact, it's probably helpful if I just quickly draw a picture of that. If this is Q1 and this is Q2, R12 is the distance between them. So, the question to you all though, don't worry, I'll give you plenty of time, we'll go back to it in just a second in case you're copying this down. If I have those two charges, just like that picture, what will happen to the potential energy if I double the distance between them? Will the potential energy double? Will it half? Will it stay the same? Or will it quarter? Will it become 1/4 of the original? Give you all about 15 more seconds or so. In 5, 4, 3, 2, 1. All right. Just like how we did. All right, so pretty good, pretty good. So we're going to do this problem the same way. I've given you all these ratio problems, and I'm going to warn you, for good or for bad, you're going to see ratio problems like this on the quiz, or sorry, on the test. I guess now is as good as time as any to mention the test to you all. The test, I already told you all the date for that. Let's quickly just jump over in case you didn't know it. I wanted to mention this anyway, but I forgot to mention it when I was going through all this stuff. The test for you all is locked in for February 16th. Heads up, the test is going to be a bunch of multiple choice. And then when I'm currently leaning, so I'm leaning between 20 to 30 multiple choice. I need to make the test and then go through it and time it myself. And then I'm going to give you probably 3 free responses. And I'm going to grade 2 out of those 3. So you get to pick which ones to solve. Good news, if you do all 3 and you get any 2 of them right, I'll take those 2 and grade those 2 and ignore the 3rd one. But that 25, those multiple choice will kind of be all or nothing. Those multiple choice questions will be questions taken from the problem sets. They will not be the really hard ones. The really hard ones that have like 10 steps to them, those are the free response ones. That way I can get partial credit for them. The multiple choice questions will be at most 2 or 3 step problems, or questions like our clicker questions. So when I come up with these, the multiple choice problems, they will be pulled from kind of the beginning of problem sets, the easier ones, and these clicker questions ones. So I just want to briefly mention that to you all. Whenever we do these, there is a reason for doing them. They're gonna be tested. So let's go ahead and put our equation, our OG, our original equation. That was K, Q1, Q2 over R. That's our original. We'll call it number 1. We go to number 2. We say that our distance is doubling. So Q1's fine, Q2's fine. Nowhere in the problem does it say those change, so they don't. But our distance, which is our variable R, doubles. So we put a 2 in front of it. 2 times, bigger. We take that 2, we pull it to the front. That 2 needs to stay on the bottom because it was on the bottom before, so it needs to stay on the bottom. So we get a 1/2 in front. That means halves. Our potential energy goes down. So the way you do these problems is you write the original, you write the new one with whatever changes in it, you pull that change out to the front, pull all whatever the changes are, multiply them, keep them in the top, keep them on the top, throw the bottom, keep them on the bottom, pull them out. Yeah. That's a great point. I told you all that it's very easy to, yep, thank you. Told you all, you can I will make mistakes many times, so you can see how tempted I was to put R squared, which means you all will be just, well, maybe you won't be as tempted as me. We'll see.
Do you say your exams are more conceptual or mathematical?
It'll be a healthy mix, probably half and half. Because we have a good few clicker questions I can draw from and a good few problem set problems, it'll probably be 50-50. Yep. And I would put this in the conceptual category to clarify. I would consider this a conceptual problem because at no point did you need to pull out a calculator. If you have to pull out a calculator, I'm not calling that conceptual. Yeah, good question there. All right, great. We already talked about this. Positive charges repel because, and this is just a graph showing what I showed you all before. When you have two positive charges, as they get closer, that energy gets larger and larger. And I told you all things want to go to lower energy, so they don't want to get closer. Whereas when we have that positive and negative, we get to a bigger and bigger and bigger negative number. And of course it wants to get to that's a smaller number. A bigger negative is a smaller number. So these graphs just show you what I said before. Helpful little visual of the same information. All right, this one's fun. We got a graph with a lot of words. I'm going to walk you all through it. I'll start the question, but I'm going to walk you through it. A proton is launched from the origin into a whole bunch of charges that are on the x-axis. This graph, shown here, shows the potential energy in microjoules of the proton as it's moving along. It is observed that the proton slows down and comes to a stop at x equals 3 millimeters. On the bottom here, we have distance. So at 3 millimeters, it comes to a stop. The question to you all is, what was the proton's initial kinetic energy at the beginning of launch? So at the end, it ends at 3 millimeters. Tell you all there is no math required for this problem. No math required. It is all visual, and it is all based on the idea that energy is conserved. So this graph shows you potential energy versus distance, and the problem asks, what was my initial kinetic energy? This may seem kind of funky at first, but once I show you all the answer, it will be a duh kind of situation. It'll make sense. If it doesn't, that's okay. We can talk to you more later. But the answer, no math required. So is the answer 1 microjoule? Is it 1.6 microjoule? Is it 3 microjoule? Let me zoom in a bit because that graph may be tricky for you all to see. So I'll zoom in and make it a little bit larger. You kind of get the gist of what's going on. I'll zoom out back again. So we have a graph, and it looks like a kind of exponential graph. As the distance is going up, my potential energy is going up, and this problem says at 3 millimeters in particular, it stops. At 3 millimeters in particular, it stops. And using that information, see if you can predict what the initial kinetic energy was. All right, I'm going to give you all about 10 more seconds, and then we'll talk through this problem. 5, 4, 3, 2, 1. All right. How'd we do? Pretty good. Pretty good. And maybe you knew why. Maybe you just saw, well, we'll see. Hope maybe it made sense, maybe it didn't. I'm going to walk through it one way or the other. But that's encouraging. I always like to know what the right answer makes me feel good. All right. So we go to our 3 millimeters, and the first thing that we can kind of do is we can see how much potential energy it has. That may be a gut reaction to do. We have x equals 3 millimeters. We have a graph. Maybe we should see how much energy we have. It's halfway between the 2 and the 4. So using your big brains, we realize that's 3. So that means that its final potential energy, its final, let me zoom out again so we can not have a bunch of craziness. UE final is 3 microjoules. All right, so how do we use this? I'm going to go ahead and make a new slide just so I have the space. Don't feel like I have to cram it all in there. I'm going to steal that graph on over. Just rewrite that. So this problem is really interesting because, again, it lets us look at conservation of energy without having to do any math, math is nice, but it's be nice when we can get a result without it. So we go back here, great. So our potential energy final was 3 microjoules. Let's go ahead and set up conservation of energy. I told you all it was a conservation of energy problem. I'm just going to give you a heads up. You're going to see that a lot. Pro tip, if you ever see something talking about velocity in this class, up to this point on our first test, if you see the word velocity, conservation of energy. There is no other problem where I'm going to be asking for velocity. It will be automatically your brain should go to conservation of energy. So that's kind of nice to know. If you see the word velocity, brain, go to conservation of energy. All right, so we have, let's set up the general form. Our energy initial, so our potential energy initial plus kinetic energy initial equals our potential energy final plus kinetic energy final, just like you all saw in Physics 1. What is our potential energy initial? Well, at 0, it is 0. At 0 distance, it's at 0. 0 microjoules. So let's just, what's our kinetic energy initial? We don't know. We're trying to solve for it. So we put 0 plus KE initial equals 3 microjoules plus, what is my kinetic energy final? Well, in this problem, there's that triangle again. That thing is weird. It keeps things lively, I guess. At 3 millimeters, it stops. That's the key word here. It stops, which means my kinetic energy final is 0 because it stops at 3 millimeters. So at the end of the day, zeros go away. There's your answer. Because it stopped, and because my initial potential energy was 0, whatever final potential energy it equals was my initial kinetic energy. So it's kind of a nifty problem that way. No math required. Once you kind of see it, you see it. If you don't, please think about it more. Come at the end of class, ask me, but that's the answer for it. Okay, let's start to do some problem set problems. We'll do probably 2, and then I think, get us to the end. If not, we'll do a couple more slides. But look at that, we're about halfway through exactly. So, as usual, in this, we're doing a couple problem set problems. So this is number 8 from R. And in case, I got questions on this, so I do want to clarify this for you all. Problem set 1 is everything that's going to be on test 1. Everything that's going to be on test 1. So week 1 was here. Week 2, here. Week 3, here. So that's week 1. So each of these corresponds to a week. Problem set 2 will work the exact same way. So we are on electric potential and electric potential energy. So this problem that we're going to be doing right now is number 8 in that problem. It says to form a hydrogen atom, a proton is fixed at a point and an electron is brought from far away to a distance of 0.529 times 10 to the minus 10 meters, which is the average distance between a proton and an electron and a hydrogen atom. How much work is done? This problem maybe, I don't know if it looks intimidating, but good news is it's a pretty simple problem for us to do. So, step 1. What is given in our problem? Well, we see proton and electron. Let's call the proton, well, actually, what am I doing? Step 0. We got to draw a picture. Here's my proton. Here's my electron. And this electron came flying in from super far away. So, let's do an initial and a final. We don't necessarily need to for this problem. So here is my initial. There was no electron to be found. It was outside the box. It didn't fit. Here's my final. I'm going to tell you all we don't necessarily need it, but it just maybe is a bit more clear. And the distance between them at the end of the day, that R is going to be 0.529 times 10 to the minus 10. Fun fact, 10 to the minus 10 meters is called an angstrom. Fun word for you all if you haven't heard it before. It's an A with a little, just jot on here. You don't need to know it. I'm going to draw it. E to the minus 10 meters is equal to 1 angstrom. You don't need to know this, but fun fact. It's an A with a little 0, get an O on top. Anyway, I'm going to erase it just so you don't get confused. So there's our picture, spot on. What's given in our problem? We have a proton and we have an electron. So let's call our proton number 1. Let's call it our electron number 2. It does not matter which is which. Charge 1, we remember that the charge due to an electron or a proton is 1.6 times 10 to the minus 19 coulombs. Charge 2 is an electron. It's the exact same number. These are coming from charge of a proton is that. Charge of an electron is that. They have the same number, just opposite signs. That's one that we'll put on our little note card for the test. You don't have to have it memorized. The other thing we know is that the distance is 0.529 times 10 to the minus 10 meters. Okay. I'm going to go ahead and copy all this and move it to a bigger slide because we're running out of room. Here's the cool thing. Once you kind of start doing the steps, once you've done step 1 and step 2, we'll throw step 2 on here while we're at it, just to prove a point. Step 2, what are we solving for? We are solving for the work. Once you've done step 1 and step 2, if you've gotten all the givens and you've identified that correctly in step 0, you don't even need to read the problem anymore. So that's why I don't copy the problem to the next slide. I don't need to. I have everything I need from it. That's the purpose of doing step 1 and step 2. It's a lot easier to look at those than it is to read a paragraph every time you want to find them. All right, step 3, what equation are we going to use? Well, if we think back, we only have a couple equations we've talked about today. See if you all, I'll give you a few seconds, see if you can think of what equation we're going to use. More fun. Give you all like 10 seconds to think about it. What equation are we going to use? There's only a couple things that work equal. What's going to be the easiest for us to work with? Give you a hint. We're going to remember that work is the negative change in potential energy. Okay? Give you a few seconds now that you got that hint. What equations do we have regarding potential energy that have to do with charges? Specifically, 2 charges, a certain distance from each other. We remember that we have that handy equation, Q1, Q2 over just plain old R, no squared. We remind ourselves that the change in potential energy of 2 charges, the amount of energy stored, which is the change in potential energy, because at infinitely far away, I mentioned this previously. We can write this down actually. Why don't we? Remember, it's final minus initial. Let's go ahead and write both of them. I told you all this is the energy stored, that this K, Q1, Q2 over R squared. Let's go ahead and write them both down, and we're going to see why originally I didn't. What was my distance initially? It's not even on the screen. So we call that infinite. Infinitely far away. If you ever see the word really far away, in physics that means infinite. And if you ever divide, as you take the limit as R goes to infinity, bam, this thing equals 0. As R goes to infinity, that second term just gone. So it was important for us to recognize that it started infinitely far away. But the end result is that we're going to get this nice, beautiful, the one that we kind of expect. K, Q1, Q2 over their distance between them squared. Not squared, no squared. Over the distance between them. Step 4 is our favorite step because it's hopefully the easiest one for us. Once you've done all the hard work of setting it up, at the end of the day, it's just plug and chug. So our work, and here's something important. We do need to put this negative here. I should have put that there before. We do need to put that negative here. Because our change in potential energy had a negative, so I needed to carry that over here. This change is final minus initial, so we do need to put that negative. So our work is going to be negative 99, that's K, times charge 1, which is 1.6 times 10 to the minus 19, times, this is a scalar, not a vector, so we do need to put in these negatives now. It does matter. When we did vectors, we didn't, but with scalars, we do. Over that 0.529 times 10 to the minus 10. We put that in our handy-dandy calculators, and it'll spit out some kind of number. Fun thing here, the negatives will cancel. I'm multiplying 2 negatives. There's a negative in the beginning. There's a negative here. So these 2 negatives will disappear. 9e9 times 1.6 e to the minus 19 times 1.6 e to the minus 19 divided by 0.529 e to the minus 10. 99 times 1.6 e to the minus 19 times 1.6 e to the minus 19. I am just literally reading off what I wrote because it's always good to double check your work because you get a very, very, very tiny answer. You get a 4.35 e minus 18. What is our unit for work? I'll give you all 5 seconds to see if you know it off the top of your head. My hint to you is it's the change in energy, and I told you all the unit for energy before. It is joules. Work has the same units as energy because it is defined as the change in energy. Okay. I am sure at least one person in this room is asking, what does positive mean? You told me previously that if I have a positive and negative, you get a negative energy, and here we have a positive when I multiply a positive and negative. So, work is different than energy. Work is different than energy. Work is how much something has to kind of expend. What is it expending? That's a good question. Energy. To kind of make this happen. So what is doing this expenditure? What is doing the work in this problem? At no point in the problem does it say a person is pushing it. At no point in the problem does it personify anything as doing the work. What's doing the work? The field. The field is doing the work here. The field is pulling these two charges together, and it is doing some work to make that happen. How do I know it's doing work? There was a force, and there was a distance that traveled along that. Anytime there is a force and a distance traveled that's in the same direction, something has to do work to make that happen. Work is literally defined as something doing a force over a distance. In this case, what's doing that? The field. The field is the thing. We made that field up so we can explain why things move. We say there's this field that exists. It's doing it. Is the field a living thing? You decide. I don't know. Personify it all you want. But the field is the one doing it. All right, we'll do one more. We'll see where we're at time-wise. We're probably going to get a couple more slides. This is going to be more of a classic. This is going to be a little bit more steps. More of a kind of a classic potential problem, especially when it comes to energy. So, I want to accelerate an electron to the speed. See the word speed here. In other words, this is velocity. Immediately, remember, conservation of energy. If you see speed, if you see velocity, I say something about it, conservation of energy. Your brain should immediately make that jump. You're going to have to use conservation of energy. All right, I want to do it by electrostatic force alone. To do so, I've devised a way to store as much charge as I'd like at a single fixed point, which will be located at a very nice distance of 0.56 meters from an electron. How much charge do I need to accomplish my goal? Okay? And I want to clarify, this is the exact speed we want to reach. We don't want to reach more than this. We don't want to get less than this. That's important, because technically, if I want to get something at the speed of sound, I could just put an infinite amount of charge there, and bam, I will definitely get that fast. I'll get much faster than that. So I want the exact amount. One of the fun things about engineering is not about building a bridge that holds up things as much as possible. Engineering is about building the cheapest bridge that just barely manages to hold everything up, because in the real world, cost is a concern. So in this case, we want just the right amount, no more, no less. You know, nothing's free in this world. So, all right, let's go ahead and kind of draw a picture here. So our first thing, we know we have an electron, and we have an initial and a final, because we're talking about, remember, our brain already said, man, conservation of energy. So our initial situation is I have an electron, which is negative, and we right off the bat, we have to think, what charge should I put there, positive or negative? And thankfully, we're really, really good at this. And we recall we are going to have to put some negative charges, a heck of a lot of them, maybe. We're going to find out exactly how many. So here's my electron. We'll call it E. You know, I'll call them Q1, Q2. Q1, Q2. In reality, this Q2 is an electron. So they start off real close, buddy-buddy, 0.56 meters apart. Call that R. And then at the end of the day, This is kind of like that last one, but the opposite. My other charge manages to stay there, and where's my electron? I can't draw off the page, but it's infinitely far away. We're going to need that infinitely far away. And you may wonder, infinity doesn't exist. That's ridiculous. This is kind of a good time to talk about infinity. In physics, obviously, in the universe, you can decide whether infinity exists or not. Technically, as far as we understand the universe, there is actually a boundary to it. It doesn't go infinite. We do, as far as we can understand, there's a boundary. So does infinite exist in this reality? That's kind of more of a philosophical question. But when we come to physics, we don't actually care if infinity exists. We care if we can approximate it as infinity. And so, for example, this wall, obviously those online can't see the wall I'm referring to, but it's behind me. This wall is clearly not infinite. However, if I move my face really close to it, I can see the edges. So as far as I'm concerned, it is infinite. Infinity is an approximation that we make in physics. If you get far enough away from something, for example, in this case, if I literally just get, I don't know, let's even just say 1,000 meters away. That's even farther than we need to go. That is effectively infinite in this problem. 1,000 meters away is effectively infinite as far as this problem is concerned. So whenever I'm talking about infinite, I'm not actually talking about literally as far away as you can possibly ever get. I'm just saying sufficiently far away that you kind of can't see it anymore. Again, kind of use the example of get your face close enough to it and it looks infinite, or like that infinite planes that we talked about. Infinite planes don't exist, but things are effectively infinite. Anyway, so my electron is, somewhere really far away, off the screen somewhere. For the purpose of saving this thing, I will draw it over here, and I will just put really far away. R equals really big. I could put infinite, but you divide by a really big number, it basically becomes 0. For those that really want, I'll put parentheses and put infinite. Because we want it to reach exactly the speed. We do not want it to get faster. You're going to see why this comes in just a second when we solve this problem. All right. So we got our picture. I need to do steps 1 and 2 on the other slide, so I will do so. I ran out of room, as I always will. That triangle. It's very bizarre. All right, so let's go ahead and write down our givens. What's given in our problem? Well, we have charge 2. That's the charge of an electron. Charge of an electron, which is negative 1.6 e to the minus 19 coulombs. We know our original distance. We'll call this R initial. If we really want, let's put R1 to initial. Just put all the things on there. Distance between R1 and 2, the two charges, and initial in the beginning equals 0.56 meters. We know our final, is really big. We'll put infinite in parentheses because it technically can't reach it. I don't want to write the word limit as it goes to infinity. I don't want to spend extra time, but effectively infinite. Effectively super far away. If we look at our picture, there's not really anything else we have. If we really want, and we may actually need this, we do know the mass of an electron, and by do know the mass of an electron, we can Google it very quickly because I don't have it memorized. Anyone want to take a guess? It was in our slide one time.
Like 1.67 10 to the negative 27.
Let's find out. Oh, you gave me the proton. The proton is 1.67. All right, so 9.11 times 10 to the minus 31. As you all solve this problem and you do conservation of energy, you would find that you're going to need that. So you're going to see that would pop up. So 9.11 times 10 to the minus 31. Okay. If you didn't realize you needed mass, you would find that out as you solve this problem. As you recall its conservation of energy, you'll see what I mean. A mass is going to pop up, and we're going to be like, okay, we need to find that. All right, so step 2. What are we solving for? Oh, there's one more variable I forgot. This guy's moving. Guy or girl, again, you define electrons as you want. V final is the speed of sound. I forgot to put that on here. Meters per second. That totally did not fit there. V final is 343 meters per second. Okay, so let's put that in our list. Again, the nice thing with conservation of energy problems is as you kind of can only set them up one way, and as you set it up, you'll see what variables you need. That's why I realized I need V final. I was thinking ahead. Step 2, we are solving for Q1. Show you where I got that in just a second. In the problem, it says, how much charge do I need to place here? How much charge do I need to gather to make this happen? So that was Q1 in our picture. Okay, so step 3, what do? Well, we see the word velocity, so we immediately think conservation of energy. Energy initial equals energy final. So potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Seeing this, maybe getting some flashbacks. Physics 1. As we're writing that down, we can jot down a couple more equations there. What is potential energy due to two charges? It's K Q1 Q2 over R. What is kinetic energy due to, well, kinetic energy is not due to any two charges, just in general. Kinetic energy is 1/2 mv squared. Okay? So, we're going to go ahead, we'll do it in step 3 still. Step 4 is all for plugging in numbers. So step 3, we'll sit in it a little bit longer. Let's plug those in and just get some big equation. Potential energy initial will be K Q1 Q2 over R1, or R initial. Let me put a little barrier here so our things don't run into each other. Plus kinetic energy initial, which is 1/2 mv initial squared, equals K Q1 Q2 over R final plus, oh no, ran out of room. Shift everything over, the beautiful of digital. And I magically have more room. Plus 1/2 mv final squared. We're writing it all out, I'm writing all the steps, but we're going to find that some of these disappear, which is really nice for us. Some of these terms will disappear. We don't need to calculate them. See if you can figure out which ones will go away. I'll give you a hint. 2 of them will. I got 4 terms up there. 2 of them will. Don't matter. 2 of them cancel out. Or not cancel out. 2 of them equal 0 due to the way the problem is set up. All right, so we look at our initial and we say, do we have a potential energy initial? Well, we have charge 1, sure, we have charge 2, and we have distance, and this will not equal 0. You can kind of see that already. Do we have a kinetic energy to begin with? In the beginning, are they moving? Nope. In the beginning, they're just sitting next to each other. I put them right next to each other, and I let them rip. But in the beginning, the velocity initial, and if we really want, we could put that over here now. The velocity initial is 0. So this term, bam, gone. Don't have to deal with it. In the beginning, they're not moving. We put them right next to each other, and then we let them fly. All right, now we go to our final situation. Do we have a potential energy final? Well, remember we said R was really big. Why? Because we wanted the exact right amount. So, I'm dividing by effectively infinite, and just like last time, bam, gone. And is my thing moving at the end? Yes. 343 meters per second. All right, so now we can get to step 4 and actually plug in some numbers. I'm just going to copy this last little, I'll rewrite it. We're at the very end. Oh yes, the beauty. Again, the beauty of digital. I can just take all my writing and make it smaller. Wow, look at that room. I did such a good job of planning ahead and leaving myself room to solve this problem. So we take that, we plug it on in, 9E9 times Q1, which is negative 1.6, e to the minus 19, times Q2, we don't know Q2, we're solving for it, divided by the initial distance, 0.56, equals, we'll put parentheses on this so we don't get it confused, 1/2 times What is actually moving in this problem? The electron is. That original charge isn't moving. It's chilling there. If we read the problem, it says, store as much charge as I'd like at a fixed point, meaning it's going to stay there. If it's fixed, it's not moving. So the electron's the only one moving. Our mass of an electron is 9.11 times 10 to the minus 31. Our final velocity, 31. Okay, I was like, that's a really small number. It's because it is. Electrons are really small. 343 squared. Okay, let's go ahead and condense a bunch of numbers together so I don't have to rewrite them as much. Combine all the numbers on the left, combine all the numbers on the right, and see what we're left with. Technically, I could solve for Q2 at this point, but again, that's a lot of numbers. So I'm going to make things a little simpler, condense some numbers down together for us. And we're going to find something really nice here. I was a little worried at first, but no, this is good. We're going to find something that I've already told you all. That's something we did at the very beginning of the problem. So 2.57, negative 2.57 times 10 to the minus 9 equals, and then half of the other. We'll just do all the other side together. Equals, my Q2, I lost it. Q2 still chilling there. Equals 5.36 times 10 to the minus 26. How do I get Q2? Just divide that number over. I have officially run out of room. I have to make a new slide. I am not going to try to cram that in there. I tried really hard. All right, last step, y'all, and we'll be good to go, and that'll be it for today. So just hang in there these last moments. As always, y'all, I know an hour and 20 minutes of physics can hurt your brain. I get it. I've been there. That is why my expectation when it comes to these classes is not that you fully learn everything in the class, but that I present everything and then you spend the time outside the class digesting it. I do not expect you all to fully understand everything I'm teaching in an hour and 20 minutes. It's just not how this stuff works. You have to spend the time to practice. So we divide both sides by that, and we get a result. We get obviously a number, but not only do we get a number, we get a negative number, which exactly matches what we expected. We expected to have a negative charge, because that's the only way they repel each other. So look at that. The math reveals reality. Double check that what I plugged in is right. How much charge do I need? Negative 2.085 times 10 to the minus 17 coulombs. Which is not very much. Shows you the power of charge. This is 100 times kind of like the charge of a proton or electron. So, just to recap, what did we cover today? What was the whole point of today? We talked about energy. We connected it to electric fields. We said that just like gravity has a potential energy, so does charges. It's another way to understand reality. Things move to lower potential energy. What's the potential energy between 2 points? K, Q1, Q2 over R. We did some problems with it. Next class, we'll look at multiple charges, and we will talk about voltage. Voltage, aka potential difference, will come from this equation. We'll explore it next time. All right. You all should be able to start the problem set on this as well, but also make certain you do the quiz. So, use your time wisely. I'd like this to go away.